Hi, it's Mr. Anderson, and right now I'm actually playing Angry Birds. Let me take care of this guy. Angry Birds is a video game where you get to launch Angry Birds at these pig-type characters. I like it for two reasons. Number one, it's addictive, but number two, it deals with physics, and a lot of my favorite games deal with physics. And so let's go to level 2. And so what I'm going to talk about today are vectors and scalars. And vectors and scalars are ways that we measure quantities in physics. And Angry Birds would be a really boring game if I just used scalars. Because if I just used scalars, I would input the speed of the bird, and then I would just let it go. And it'd be boring because I wouldn't be able to vary the direction. And so in Angry Birds, I can vary the direction, and I can try to skip this off of... Nice. I can try to skip it off and kill a number of these pigs at once. Now, I could play this for the whole 10 minutes, but that would probably be a waste of time. And so what I want to do is talk about scalars and vector quantities. Scalar and vector quantities, I wanted to start with them at the beginning of physics because sometimes we get to vectors and people get confused and don't understand where did they come from. And so we have quantities that we measure in science, especially in physics, and we give numbers and units to those, but they come in two different types, and those are scalar and vector. To kind of talk about the difference between the two, a scalar quantity is going to be a quantity where we just measure the magnitude. And so an example of a scalar quantity could be speed. So when you measure the speed of something, and I say, how fast does your car go? You might say that my car goes 109 miles per hour. Or if you're a physics teacher, you might say that my bike goes, I don't know, like 9.6 meters per second. And so this is going to be speed. And the reason it's a scalar quantity is it simply gives me a magnitude, how fast. How far, how big, how quick. All those things are scalar quantities. What's missing from a scalar quantity is direction. And so vector quantities are going to tell you not only the magnitude, but they're also going to tell you what direction that magnitude is in. So let me use a different color maybe. Example of a vector quantity would be velocity. And so in science, it's really important that we make this distinction between speed and velocity. Speed is just how fast something is going, but velocity is also going to contain the direction. In other words, I could say that my bike is going 9.08 meters per second west. Or I could say this pen is being thrown with an initial velocity of 2.8 meters per second up or in the positive. And so once we add direction to a quantity, now we have a vector. Now you might think to yourself, that's kind of nitpicky. Why do we care what direction that we're flowing in? And I have a demonstration that'll kind of show you the importance of that. But a good example would be acceleration. And so what is acceleration? Acceleration is simply change in velocity over time. And so acceleration is going to be the change in velocity over time. And so I could ask you a question like this. Let's say a car is driving down a road and it's going 23 meters per second and it stays at 23 meters per second. Is it accelerating? And you would say, no, of course it's not. Let's say it goes around a corner and during that movement around the corner it stays at 23 miles per hour. Well, what would happen to the scalar quantity of speed around a corner? It would still be 23 meters per second. And so if you're using scalar quantities, we'd have to say that it's not accelerating. But since velocity is a vector, if you're going 23 miles an hour and you go around a corner, are you accelerating? Yeah, because you're not changing the magnitude of your speed, but you're clearly changing the direction. And so a change in velocity is going to be acceleration. And so you are accelerating when you go around a corner. And so that'd be an example of why in physics, I'm not trying to be nitpicky, I'm just saying that you have to understand the difference between a scalar quantity, and then which is just magnitude, and a vector, which is magnitude and direction. There's a review at the end of this video, and so I'll have you go through a bunch of these, and so we'll identify a number of them. But for now, I wanted to give you a little demonstration to show you the importance of scalar and vector quantities. And so what I have here is a 1,000 gram weight, or 1 kilogram weight, and it's suspended from a scale, and I don't know if you can read that on there, but the scale measures the number of grams. And so if this is 1,000 grams, and this measures the number of grams, and it's scaled right, it should say, and it does, about 1,000 grams is the weight of this. Now, a question I could ask you is this. Let's say I bring another scale, and so I'm going to attach another scale to it. And so if we had one mass that had a mass of 1,000 grams, and now I have two scales that are bearing the weight of that, and I lift them directly up, what should each of the scales read? And if you're thinking, well, it's 1,000 grams, so each one should read 500 grams. Let me try it. The right answer is, yeah. Each of the scales weigh right at about 500 grams. And so that should make sense to you. In other words, 500 plus 500 is 1,000, so we have the force down of the weight, force of tension that's holding these in position. And so we should be good to go. The problem becomes when I start to change the angle. And so what I'm going to do, and I'm sure this will go off screen, is I'm going to start to hold these at a different angle. And so what if I look right here, I now find that it's at 600. And so this one is at 600 as well. And so as I increase the angle like this, we'll find that that will increase as well. And so when I get it to an angle like this, I have 1,000 gram weight, and it's being supported by two scales now that are reading 1,000. And it's going to vary as I come back to here. And if you do any weightlifting, you understand kind of how that works. And so the question becomes, how do we do math? The problem with this then is that the numbers don't add up. And so if I've got a 500 gram weight, excuse me, 1,000 gram weight being supported by two scales, it made sense that it was weighing 500 each. But now we all of a sudden have 1,000 gram weight being supported by two scales that are each reading 1,000. And so this doesn't make sense, or the math doesn't make sense. And the reason why is that you're trying to solve the problem from a scalar perspective. And you'll never be able to get the right answer because it's going to change, and it's going to change depending on the angle that we lift them at. So to understand this in a vector method, and we'll get way into detail, so I just kind of want to touch on it for just a second. What we had was a weight, so we'll say there's a weight like this, and we'll say that's 1,000 gram weight. And then we have two scales, and each of those scales are pulling at 500 grams. And so if you add the vectors up, so this is one vector and this is another vector, so each of these are 500 grams, so I make them 500 in length, then we balance out. In other words, you have the balancing of this weight with these two weights that are on top of it. Now if we go to the vector problem, in the vector problem, again, we had 1,000 gram weight, so 1,000 grams in the middle. And then we had a force in this direction of 1,000 and a force in that direction of 1,000. So we had the force down of 1,000, but we had a force of 1,000 in this direction and a force of 1,000 in that direction. And so if you start to look at it like a vector quantity, imagine this, that we've got a weight right here, but you have to have two people pulling on it. And so it's like this tug of war where it's not just in one direction, but it's actually in two. And so you can start to see how these forces are going to balance out, but only if we look at it from the vector perspective. Let me show you what that would actually look like. So if we put these tails up, this would be that force down of 1,000 grams. This would be the force of the weight. But we also had a force in this direction. So I'm doing the same rule where I'm lining up my vector from the tail to the tip and the tail to the tip. And so that diagram that I had on the last slide, I'm actually moving this one force, and you can see that they all sum up to 0. And so the reason I like to start talking about vectors and scalars with this problem is that you could never solve the problem if you're going to go at it from a scalar perspective. And we're going to do some really cool problems. Let's say I'm sliding a box across the floor. But how often do you slide a box across the floor and actually pull it straight across like that? If you're like me, you're pulling a sled or something, you're normally pulling it at an angle. And once we start pulling at an angle, it becomes a totally different force. And we can't solve problems in the scalar way. We have to go and solve it from a vector perspective. And so that's the importance of vectors. Now, it's a huge thing. So there are lots of things that we can measure in physics. And so what I'm going to try to do, hopefully I can get this right, is go through and circle all the scalar quantities and then go back and circle all the vector quantities. And so if you're watching this video, a good thing to do would be to pause it right now, and then you go through and circle the ones that you think are scalar and then vector, and then we'll see if we match up at the end. Scalar quantities, remember, is simply going to be magnitude. And so the question I always ask myself when I'm doing this is, okay, does it have a direction? And so length is simply the length of a side of something, and so I would put that in the scalar perspective. This is kind of philosophical. Does time have a direction? I would say no. Acceleration, we already talked about that. That's changing in velocity. What about density? The density of something, that definitely is a scalar quantity. If I say the density of that is 12.8 grams per cubic centimeter north, that doesn't make sense at all. Where's some other scalar quantities? Temperature would be a scalar quantity. It's just how fast the molecules are moving, but it's not in one certain direction. Pressure would be another one that's scalar. It's not directional. It's not in one direction the pressure is. Remember, pressure, air pressure is the one that I always think of, is going to be in all directions, so we wouldn't say that. Let's say mass. The mass of something is going to be a scalar quantity as well, and so it doesn't change. Now weight, and we'll talk more about that later in the year, would actually be a vector quantity. Let's see if I'm missing any here. No, I think this would be good, so let's change color for a second. So displacement is how far you move from a location, and that's in a direction. So we call that a vector quantity. Acceleration I mentioned before. Force is going to be a vector, and we'll do these force diagrams, which are really fun, later in the year. Drag is something slowing you down. So if you're a car, it's what's slowing you down in the opposite direction of your movement. So the direction is important. Momentum is a product of velocity and the mass of an object, and lift we get from like an airplane wing. That would be a vector quantity because it's in a direction. And so these are all vector quantities, the ones that I circled in red, but there are way more that we're going to find out there. And scalar quantities, remember, it's simply just magnitude, or how big it is. And so as we go through physics, be thinking to yourself, is this a scalar quantity or vector? And if it's vector, my problem is a little bit harder, but like Angry Birds, it's more fun when you go the vector route. And so I hope that's helpful, and have a great day.